magnetic flux. So magnetic flux is the number of turns of the solenoid. Okay, number of turns of that copper wire. Times the magnetic flux, which is measured in Tesla times meter squared, divided by the change in time. And the magnetic flux is B, which is the strength of the magnetic field, which is in Tesla. And the area of that coil, the area here, because if I've got like spaghetti strings and I can put them through, I can get more in if this coil was very, very big. Okay, so the area, and then cos theta, and we say, okay, where does this cos theta come from? Well, it's the angle between the magnet. Can you see if the magnet is here? I can get lots of field lines. There are tons of field lines going in there. Make sure your field lines don't touch each other. Tons of field lines going in there, coming out there. And the movement of this backwards and forwards will cause EMF. So, how is this cos thing related? Well, if this, now if I draw my coil and I draw a line parallel to it, and it's called like a normal force, then the smaller the angle between this normal force, that's not quite perpendicular, this is perpendicular, to the magnetic field. Can you see now it's parallel? Now I can just go in. This makes kind of an angle. There's almost no angle here. So if cos, what is cos of 0? And let's quickly put that in. Cos of 0 is 1. And we know that from our cos graph, that it starts at 1. Okay, so 1. And here's my amplitude or whatever. So here's 1, here's 0. Where's that 0? That 0 is at 90. So what if I take my battery, my magnet, sorry, and I move it up? What's the angle going to be? So cos of 0, if the angle is 0, is going to be 1. If I move my magnet up, can you see I moved it slightly up? Very slightly. So now what happens is I've got my normal force and I've got my height. What a bit of a height above there. Can you see that? Yes, I'm going to get some spaghetti lines through there. And I'm going to get a few spaghetti lines through here, but not many. Not as many as the first one. So my angle is going to be a little bit greater between this normal force from inside this solenoid. Normal force means 90 degrees to it. And my angle is going to be a bit bigger. And what does that mean? If I say cos of 0 is 1, what is cos of 90 degrees? Well, if I put it on my calculator now, and you can put it on a calculator as well, cos of 90 is 0. What does that really mean? If I've got a 90-degree angle to here, and the battery's at a 90-degree angle, can these field lines get through there? No, there's no area to get it through. It can't move into the coils. It can't move into that stuff and make field lines. The spaghetti is going to hit those earrings or bracelets or whatever it is, and the spaghetti is not going to be able to go through. Okay, so think of spaghetti. So what does this mean? That the greater the angle is between 0 and 90, the greater the angle is, let's pick another angle. Cos of 60 is root 3 over 2. And root 3 over 2 in terms of commas, cos 60, come on, cos 60 is 0.5. Oh, cos 60 is 0.5, not root 3 over 2, that's silly, sorry. It's 1 over 2, is 1 over 2. And then cos 30 is root 3 over 2. So cos, oh, I'm just using my calculator. I think it's 0.6 something. So you can see that the smaller the angle, the greater the number after I've cosed it. The smaller the angle, the greater the number. And that makes sense, because if it's B times A times cos theta, I have something like 30 times Tesla, I don't know what it is, 30 times, maybe it's 2, and this is a circular one, so this will be pi r squared to find the area. But say for instance you can have a square solenoid, so let's say 2 times 2, which is before, times cos of theta. Now if cos of theta is 0, this whole thing is going to become 0, and there's going to be no magnetic flux. Can you see? There's no magnetic flux. Those spaghetti strands can't get in there. Okay, so that's going to be 0. If this angle is smaller, the smaller the angle, the greater the magnetic flux. The smaller the angle, the greater magnetic flux. So if I say cos of 60, which is a half, cos of 60, let's see here, this is not quite 60, this is about 30. So this would be about a half. So if I say 30 times 4 is 120 times a half is cos of 60. Half, which should be 60. Weird numbers. So then you go, but cos is, what is cos? Cos is adjacent over hypotenuse. And you say, but where's the adjacent and where's the hypotenuse? Well, this is the angle, and let's go and look a little bit further. And I've brought it up even more. Can you see? It's not here anymore. It's not here anymore. It's up even more. So there's more height to this thing. There's more height to this thing. Now, if I have, this is the normal, and this is the angle between the normal. It's between the magnets and the normal. Okay, so between the magnets and the normal, I've got to have, this is kind of how high it is. Although this is height, but it's kind of how high and what angle and how high it is from the normal. And if I say cos theta, cos would be the adjacent to theta. Oh, it's taking a long time to explain, sorry. This would be cos theta would be adjacent over kind of how high and what angle it is of hypotenuse. How high it is and what angle it is. Not just how high, because if it was just how high, next one. Oh, no, the third one. If it was just how high, can you see that this one's high, but it's not high over here. If it's high over here, not many magnetic lines can get through here. But if it's high here, some magnetic lines can get through here. So it doesn't only determine on how high it is, but how far, not really how far, but what angle it is. And this is produced by this angle to the normal. The normal is 90 degrees from these coils, from the solenoid. Okay, so I've got cos of theta, and cos of theta here would be quite big. Cos of theta would be, maybe, I want to put it at, let's pick one, and let's say cos of theta would be 75, well, theta would be 75 degrees. So cos of theta, if theta is 75 degrees. So in your calculator, you're going to put cos of 75. And what's cos of 75? It's 0.2 or 0.25. or 0.26. So if I've got 30 times 4 times 0.26, or if I got 30 times 4 times 1, if the magnet was here, why do I keep saying battery? If the magnet was here, which is bigger? This one. Therefore, my phi or phi, fofum, my magnetic flux would be bigger, would be stronger. And that makes sense because more lines can go through here, the more magnetic lines, than it can through at this weird angle. Maybe 1 or 2 only go through there. Okay, let's look back. And what if you say, well, what if I put it underneath? Well, I still have a normal or a perpendicular normal to my coil, and I've got a line here, and that's my angle. So my angle's theta, and how far away from here in terms of height and distance, and maybe that would be, okay, I wouldn't say negative 30, but I would say 30 in the other direction, and cos of 30 would be cos 30 is 0.866. It's that root 3 over 2. So that would be 0.866. And if I say 30 times 4 times 0.866, that would be more. If this was a 30-degree angle, then that 30 times 40 times 0.5, which would be a 60-degree angle, which would be more here. And a 90-degree would be here, which means nothing would get through. So what we've got to understand is that cos comes from the normal, the magnet's angle to the normal, that's made here. The magnet's angle to the normal. So adjacent, which is the normal, over hypotenuse, which is the angle and the distance from and the height, all joined together from the normal. Okay, less can get through here. I can't get any through here, so cos of 90 would be 0 again. Cos of 90 would be 0, which means my magnetic flux would be 0. But cos of maybe 15 degrees, let's check that. So cos of a very small angle would be 0.97. And cos of 0 degrees, in other words, it's parallel. I don't want to do that because that might be the direction of the current. But parallel means 0 degrees between the normal and the magnetic lines. That would be 1. So 30 times 4 times 1, because cos of 0 is 1 from my cos graph.